Our own galaxy that we're inside of is called the Milky Way. In fact, the word galaxy comes from the Greek word for milk, gala. On clear nights, especially without the presence of the moon, you can see the disk of the Milky Way. You'll notice billions of stars and lots of gas and dust, too. Our eyes might not capture as much light as a long exposure photograph like this one, but if you sweep the area of the Milky Way, even in binoculars, you will see a magnificent view. The Sun, of course, is not in the center of the Milky Way galaxy. In fact, it's about 27,000 light years from the center, which corresponds to 8 kiloparsecs. The Sun is orbiting the center of our galaxy with a tangential velocity of about 220 kilometers per second. It takes about 220 million years for it to orbit once. And based on the age of the Sun, we think it's done about 20 orbits and will probably do about another 20. The ecliptic, which is the orbital plane of the planets in our solar system, is tilted by about 60 degrees with respect to the galaxy's disk. Three main parts of the Milky Way galaxy and of any spiral galaxy are the disk, bulge, and halo. The Milky Way's disk is about 100,000 light years, or 30 kiloparsecs, across. It has spiral arms, either from density waves or from self-propagating star formation. The Sun is not currently in a spiral arm, but between spiral arms, which gives us a more transparent view from Earth at our surroundings. To put this size into perspective, Arne and Schneider's textbook says that if the Milky Way were the size of the Earth, then our solar system would be the size of a cookie. At the center of the Milky Way is a bulge. This bulge is a dense concentration of stars. It also has gas and dust that constitute 15% of the mass of stars. The bulge is elongated, so we could describe it as a bar, making the Milky Way a barred spiral galaxy. And there is a black hole, Sagittarius A star, in the nucleus of our galaxy. Then there's also a spheroidal halo that extends out to large distances. There isn't a precise edge of the galaxy, but the density tapers off. In the halo are older stars in globular clusters. The oldest stars in the Milky Way seem to be about 13 billion years old, almost as old as the universe. The newest stars are still forming. The average rate of star formation in the Milky Way is 7 to 8 stars per year, but this rate is slowing down compared to the early years. In general, when you look at a region, bluer means newer, and redder means older. As we begin to look at other galaxies, first it's good to have an idea of what galaxies are in our local group, the neighborhood around us. The local group with capital letters is what this neighborhood is called. It is a cluster of galaxies. The three large galaxies in the local group are the Milky Way, Andromeda Galaxy, which is a little bit bigger than the Milky Way, and the Triangulum Galaxy. There are also a lot of dwarf galaxies and other structures, such as the Large and Small Magellanic Clouds. The Large and Small Magellanic Clouds in the southern celestial sphere are relatively close to the Milky Way and will eventually spiral in and merge with the Milky Way. Later on, the Andromeda Galaxy will also collide with the Milky Way. That will happen in about 4 to 5 billion years. The Andromeda Galaxy is the most distant object that can be seen with the naked eye under optimal conditions. To measure distances to other galaxies, parallax doesn't help us anymore. These objects are too far for parallax to tell us anything, so we need to use other methods to determine the distance. And some of these methods are known as standard candles. Cepheid variables were of the first standard candles. Recall that their period is related to their luminosity, and then their luminosity can be connected to their apparent brightness by the inverse square law, so we can know the distance away from them. Another method that is used for galaxies is the Tully-Fisher relation. The galaxy's rotation speed can be found from a spectrum using Doppler spectroscopy. We can measure the redshift or blue shift of the galaxy as a whole, and we can measure the redshift and blue shift of the different sides of the galaxy, the different spiral arms. Then an estimate of the galaxy's luminosity can be made. And then a distance can be calculated based on that luminosity and apparent brightness using the inverse square law. Many of these standard candles or methods in the cosmic distance ladder have contributed toward establishing the Hubble-Lamaitre constant. Using the Hubble-Lamaitre law is the easiest way to determine a galaxy's distance from us. Most galaxies do follow that trend, but there are plenty of outliers, and so other methods should be used in conjunction with the Hubble-Lamaitre law. Spiral galaxies make up about 70% of all galaxies. Some spiral galaxies have a bar in the center and are called barred spirals. Elliptical galaxies make up most of the remaining 30% of galaxies. Giant elliptical galaxies are the result of merged galaxies, but there are also dwarf elliptical galaxies. About 1% of galaxies are classified as irregular galaxies. Edwin Hubble originally had a tuning fork diagram to explain the types of galaxies. At that time, he thought that there was a sort of evolution from galaxies from the elliptical part to one of the spiral parts, either with a bar or without a bar. That's why sometimes you might hear elliptical galaxies called early type galaxies and spiral galaxies called late type galaxies. Currently, we don't think that the tuning fork diagram describes the evolution of galaxies, but we still use these labels in classifying them. E for elliptical, from 0 to 7, depending on how elongated it is. S for spiral, B for bar, A, B, and C. There's also D, not shown on this diagram, depending on how the spirals are seen. And then in the middle of all of it is S0, a lenticular galaxy, kind of a mix between elliptical and spiral. We mentioned globular clusters earlier, so I just wanted to clarify that a globular cluster is a lot smaller than a galaxy. It doesn't have as many stars, even though it is a high concentration of stars. A globular cluster is usually found in a galaxy's halo, and the Milky Way has about 150 globular clusters. In fact, early efforts to map out the Milky Way galaxy used how bright or dim globular clusters were. About 10% of galaxies are emitting large amounts of energy from their nuclei. The cause of active galactic nuclei is most likely supermassive black holes. Active galaxies with extremely luminous nuclei are called Seyfert galaxies, which sometimes even eject gas in jets. There are also radio galaxies, which emit large amounts of energy in the radio part of the spectrum. These are usually elliptical galaxies. They can form radio lobes on either side of the galaxy. The radio output is due to synchrotron radiation, because these galaxies have strong magnetic fields. The name quasar comes from quasi-stellar radio source. Quasars look like dim stars, but they emit a lot of energy in the radio part of the spectrum. They are actually active galaxies that are extremely luminous and extremely distant. Some of them are more than 10 billion light years away. That means it's taken 10 billion years for their light to reach us. So they're very old. When we look at quasars, we're looking into the past. Why don't we see any nearby quasars? They are probably now all galaxies in the spiral or elliptical form. Their extreme activity has by now faded away. Because quasars are all so distant from us, a lot of them are behind other massive objects. And through gravitational lensing, we see multiple quasars when it's really only one. The image on the right shows what is called the Einstein cross. The object in the middle of this is in the foreground, and then there are four other objects on different sides, which in fact are all the same object, a quasar. Its light is bent around the object in the foreground on four different sides. So we see it four times. When we look at spiral galaxies, we can expect the inner parts of the galaxy to orbit faster than the outer parts. This is what we would expect from Kepler's laws. But we have found that the orbits of stars around the center of a galaxy do not follow Kepler's laws. The plot on the right shows stars' orbital velocity, the vertical axis, by its distance from the center of the galaxy in its horizontal axis. It's lower near the center because there isn't as much mass enclosed in that circle. And there's more mass enclosed as we start to go out. But we would expect it to reach a peak and then taper off because the outer parts of a galaxy are not as luminous as the inner parts, so there should be less mass there. But that's not what we observe. We normally observe a galaxy's rotation curve to remain pretty flat. We don't observe what mass there is that could make it this way. So we call that dark matter. Dark matter doesn't emit any electromagnetic radiation, and it only interacts with stars and gas through gravity. We don't observe the effects of dark matter at all on the scale of our solar system, but when we talk about the entire galaxy, it seems that there is about 8 or 9 times as much dark matter as there is ordinary matter. We still don't have a good grasp of what dark matter is, but there are a few hypotheses. One hypothesis is the MACHO hypothesis. MACHO stands for Massive Compact Halo Object. These would include planets, brown dwarfs, old white dwarfs, neutron stars, and isolated black holes. But we should be able to detect these through gravitational lensing. We do detect some of them, but not enough to account for all this dark matter. Another hypothesis is the WIMP hypothesis, which stands for Weakly Interacting Massive Particle. When it was discovered that neutrinos have some mass, well, that constitutes some part of dark matter due to WIMPs, but not nearly enough. There could be other WIMPs, though. When we look at merging galaxies, as these pictures on the left show, we can make maps of the dark matter in blue. And we see that dark matter does not experience the kind of friction that normal clouds of matter experience when they collide. And we have observed one entire galaxy that seems to have no dark matter at all. There have also been efforts to modify Newtonian dynamics to explain away dark matter and say it doesn't even exist. It's just that we don't know gravity well enough. And while this is unlikely, it is still possible. Dark matter today remains quite a mystery.